Okay. All right, so with inferential statistics, we want to remind ourselves, first of all, these scales of measurement. And by the way, a lot of what we're doing today is not necessarily in your book. So you will want to take note of things here. But remember the scales of measurement. Can you guys remember the 4 scales that we talked about?
What they were.
All right, go.
Can you give me a like
Hang on. There's ordinal is one.
Intermediate.
What? Nominal, that's the lowest level. What? Interval and ratio. Very good, okay? Nominal, where we're numbering things, okay? We're just, basically we're counting stuff, putting it into categories and we're counting them. Alright? So we could, number how many people are from each different country or something like that. That would be a nominal scale. Ordinal, we're talking about ordering things, either by ranking them or ratings as well. Okay? When you guys get IB scores, 1 through 7, those are ordinal scale values because there's not a consistent difference between someone who got a 1 and someone who got a 5. Okay? Or even a 4 and a 5. Because you could have people who scored very, very close to each other. It's just they were right near the border between a 4 and a 5. Or you could have had one person who almost got a 3 and another person who almost got a 6, and their scores are way away from each other. Alright, but they still have a 4 and a 5 as their score. Those are ordinal scale values. Okay? You said interval as well. Values of a variable ordered on a scale that has equal intervals. Now, the difference between a 4 and a 5 is the same as the difference between a 5 and a 6, and a 6 and a 7, and so on. Okay? We had mentioned temperature. Test scores are this way as well. When you get a 92% on a test or an 85% on a test, the difference between an 85 and an 86 is the same as the difference between a 92 and a 93. And then, as you guys mentioned, the last one is the ratio score, or ratio scale. Here the key is, it's basically an interval scale except it has an absolute 0. Okay? And what that absolute 0 allows us to do is talk in terms of comparisons like 45% more or twice as much. One thing this is an important distinction to make, particularly as you guys work on your IAs. If you're going to do a statistics exploration, which I would recommend, if you're dealing with interval scale values, you can't talk about things being twice as much.
I don't understand how does having an absolute 0 allow you to say that it's twice as much?
Well, for example, think of it, let's use the example of a test. Your grade on a test versus the number of points earned on a test. Okay? It's kind of a fine distinction here, but if you're talking about your grade and you got a 75%, that doesn't mean you know 3/4 of everything there is to know about that topic. Right? And if you get, let's say you got an 80%, someone else got a 40%, that doesn't mean you know twice as much about that topic. It just means you happen to get twice as many right on the test. Okay? But that, you're talking about points. In points, there would be a ratio scale because there is an absolute 0 amount of points.
You can get a 0
Okay.
on a test though.
Huh?
You can get a 0 on a test though.
Yes, but you're talking about the difference between points earned and like knowledge. Okay? The fact that you got a 0 on the test just means you missed all the questions. It doesn't mean that you know absolutely nothing about that topic. Does that make sense? It doesn't mean you have
So
zero
like
knowledge.
if someone gets a 50 and someone gets 100%, like if Will gets a 50 and I get 100, I can't say I'm twice as smart as him, but if you got 50 points and I got 100 points, I could say I was.
Well, no, you could just say that you got twice as many points as him. That's all you can say. All right. So another example is like temperature. Okay. You know, if it's 40 degrees in Cleveland and it's 80 degrees out down here, I wouldn't say it's twice as hot, even though people do say that all the time. They say stuff like it's twice as hot here as it is there. That's
Why doesn't that make sense though? Because you can't just have like
well because.
two cold
Because,
There's no absolute zero to make that comparison.
Yeah, on the Fahrenheit scale, you can't do that, because if you took like the amount of joules in the average square foot of air, it would not be twice.
Either way, you're talking about a scale that doesn't have a zero.
Why does it have a 0 that can be 0?
Because 0 degrees.
But 0 degrees is a,
arbitrary.
you can have a value of 0, but that 0 is
Do
arbitrary.
you know where 0 degrees Fahrenheit comes from? Fahrenheit took a bucket of water with ice, poured salt in it, and stirred it to try and get it as cold as he could. And he said, "This is 0."
Were you there?
No, but he reported that.
Either way, it's arbitrary. That's the point. Okay? An interval scale may have a value that equals 0, but it's arbitrary.
So what is the absolute?
Okay.
The absolute 0 is like.
Absolute 0 means that there literally is nothing at that level. Like the number of points you earn.
Okay.
You can earn 0 points, but it doesn't mean you have 0 knowledge. Okay, knowledge would be like, well, I don't think it would even be an interval scale, but ratio has to be things that you could have nothing of. All right. So those are scales of measurement. There are two main things that we do with inferential statistics. One is try to determine a correlation. Okay? We try to determine correlations. And what a correlation is it's a statement that there is some relationship here. There is some connection between these two variables. Okay? Now, the key thing that we have to identify here is statistically significant. All right, and we're going to talk about what that means when we're looking at our hypothesis testing. We want to show whether or not there is a statistically significant relationship. That doesn't necessarily mean there's going to be a strong relationship. It's just statistically significant. There's a difference there. Okay, you can have something that actually shows what would be considered a strong relationship, but it's not strong enough to be statistically significant because maybe you don't have very much data that you're drawing that from. Okay? For example, if I just picked 5 of you and I was trying to determine a correlation between something, height and GPA or something. If I picked the right 5 people, I could get a really good, strong correlation between height and GPA. However, in order for that to be statistically significant, number one, it would have to be from a random sample, so that, but also, it would have to be very, very high because I only have 5 people. And we'll look at what are called critical values later on. Those are determined on how many people you have involved or how many data points you have involved. Okay? Now, there are 3 main tests. We're going to look specifically at one. But I show, and I'll tell you a little bit about all 3 because none of these tests are really that hard to run. But all of these tests would be good examples of topics that you could use for your IA. And it's nice because you can make it about something that's totally unrelated to math, but you run the math to show a correlation or disprove a correlation. Anyways, we have the Pearson product moment. That's what we're going to be doing, the Pearson's R value. We'll talk about that a lot more tomorrow. The Spearman rank is an interesting one. This is specifically designed for ordinal data. Okay? This is what you would use when you have two different things that are both rating or ranking certain items. And you would try to determine if they are related in the sense that they're rating things consistently. Okay? I don't know, have any of you competed in things where you were rated like by a judge on a point system or something like that? And it's kind of subjective. And you might get one judge that's really kind of easy and everyone has pretty high marks. And then you have another judge that's pretty, harsh and you have lower marks. The fact of the matter is, when it comes to who won, it really doesn't matter what the numbers were. It matters what order they put people in, right? So, one person could have all their scores at, 85 to 90 out of 100. The other person could have all their scores between 75 and 90. But as long as the people are in the same order, we could say that there's a relationship and that they're judging it fairly, or they're judging it equitably. There was, I remember when I was little, there was a lot of debate in the Olympics. One of the sports that's really more of a competition than a sport, because sports technically have, well, I won't get into that. But anyways, things that are judged aren't, by purest definition, sports, even though they take a lot of athletic ability. So one of those was figure skating.
So like,
And there was a lot of speculation and whatnot that certain judges were intentionally giving skaters from one country really low marks and giving skaters from their own countries high marks because they wanted their people to win and they wanted their top competition to not do as well. Okay? And it wasn't like a drastic, like they're giving them a 1 or something, but it was always a little bit lower. And it was at least suspicious. But this is the kind of thing that they could run. They could compare that judge to other individual judges. And I'm sure they probably did do something like this at that time to compare, all right, is this judge significantly, the same as the other judges? And they would just, the thing is with this, you have to run 2 at a time. So you put them in pairs, do all the possible pairings, and then see if there's one judge in particular who seems to be askew from the rest. You could also use this if you had, let's say you had 2 judges. If they were significantly different, then you might get a third opinion. Get a third judge in there to judge and see what they say. Okay? But it's really kind of an interesting test. The last of these is a chi-squared. Okay? There are 2 of these. They're kind of actually 2 types of chi-squared tests. One is with a contingency table, and this is where you're comparing categorical type of data. For example, someone in their IA last year compared what sport a person played and GPA. Okay? Did the sport that you play have a relationship with your GPA? And the cool thing about this is you're dealing with categories, so it's actually nominal data. At least some of it's nominal data. You play basketball, or volleyball, or softball, or whatever, soccer, and you're just counting how many people are in those categories. Then you're also comparing them with different ranges of GPA, and what you're trying to see is there a relationship between one of these and in the variable involved. In this case, it was GPA. There's another type where you're comparing actual data with expected data. Like, for example, you're given certain demographics about an area, okay? Let's say you're told that a certain area, is balanced politically. In this particular town, it's like 40% Republican and 40% Democrat and 20% Independent. So you decide to test that claim. You could go out and survey a whole bunch of people. Which of the three are you? And then you could run it. What do I expect with the number of people I surveyed and the percentages I was given? What would I expect to happen? And then what actually happened? And you can actually use the chi-square test to see if there is a significant relationship between them. Okay? And if not, then you could say, okay, probably the percentages that I was told are suspect, or maybe I had a bad sample. That's possible too. But on all of this, we're assuming that you would get a random sample. We'll talk a little bit about that as well when we start the IA. Those of you who do statistics, I'll talk with you about sampling and make sure that you guys are getting good data to use. Another thing we can do with inferential statistics is look for significant differences. Okay? Is there a statistically significant difference? And for this, we can use t-tests. And there are two types of t-tests. One is for independent samples. This would be like if I compared the quiz scores from the class in 5A to you guys, and I wanted to say, is there a statistically significant difference in your quiz scores? I could do that using a t-test for independent samples. If I wanted to look at, say, a before and after type of a situation, I could use a t-test for dependent samples. This is the kind of thing that's used in, that can be used in medical research. For example, we're going to test if this medicine is actually lowering someone's blood pressure like it's supposed to. So what they would do is they test everybody's blood pressure, get those numbers, and then with the same people, they would give them this medication and test their blood pressure after they've been on it for a while. And just because there is a change doesn't mean it's a statistically significant change. So they would use a t-test for dependent samples to determine is the before and after effect of using this medication statistically significant. Is the medicine doing something good here? Or is it doing something at all? It actually could be in the opposite direction too. All this tells us is that there is a significant difference. Okay? The other one is the ANOVA test, and it's a similar idea, but the ANOVA test takes into account more than just two things. You can have a number of different variables coming into play with an ANOVA test. Okay? Now, if you want to look at specifics of these tests, I did post something on our class website. If you go to, here we go. If you go to important class documents, I changed all the font. There we go. Down here, there is Introduction to Inferential Statistics, Correlations and Differences, and it has some examples of some of those problems, because we're not going to do all those tests in our class. one thing that you need to make sure you identify in any of these tests is you need to identify what the dependent variable and what the independent variable are. Okay? So, for example, the dependent variable is the thing that we're trying to measure, the outcome. And the independent variable, which you may hear called sometimes the experimental variable, this is the thing that we're manipulating or that we're changing to see what effect it has on the dependent variable. Okay? So, for example, we could say, we want to test the impact that sunlight has on a growing plant. Okay? How many hours of sunlight? So, we're going to vary the amount of sunlight that something gets, by covering it up or putting it in a closet or something like that. That's going to be the independent variable. How much it grows would be the dependent variable. Yes? So all this kind of lays the groundwork, and I just wanted to kind of touch on all of these so that you would have an idea, and again, you would have a good selection of potential IA strategies or things that you could use for your IAs. Okay? So let's start talking about correlation specifically. Okay? We already mentioned that correlation refers to a relationship between two variables. Correlation. Alright? Correlation. We're going to be looking specifically at ones that follow a linear relationship or a linear pattern. And the question we want to ask is, how closely does our data, or how well does our data follow the linear pattern? As our dependent variable, as our independent variable increases, does our independent variable change consistently? Now, to illustrate this, let's talk about, or let's see some scatter plots. First of all, one thing you could have is perfect correlation. Now, in real life, this rarely, if ever, happens. Okay?
My experiment today.
When you don't manipulate the numbers?
Yeah, and for some reason we had 0% error doing 5 trials for each part of the experiment and a perfect linear correlation.
Wow. Now, this one is perfect positive correlation. How can you tell it's positive?
It goes that way.
Yeah, we're going up. It's increasing. Our dependent variable is increasing as our independent variable increases. Okay? So that's perfect positive. Okay? You could also have a strong positive correlation. Notice here the points are all pretty close to the line. You can see that you have this linear trend, and they're all pretty close to this line. By the way, we would call this line a line of best fit. Okay? So that's a strong positive correlation. A moderate to weak correlation would look something like this. You'll notice we still have a general trend, but we've got a few outliers over here. Okay? We've got a few outliers and whatnot. They're not real close to the line. Some are on the line, but they're not super close to the line. That would be a moderate to weak correlation. Now, even though something is moderate or weak correlation, it still could be statistically significant. Okay? In fact, a lot of times we'll see, moderate or even weak correlations where if it came from enough data points, it would still actually be significant. Okay? And the idea there is, if we have so much data, even though it's just kind of loosely following this pattern, okay? There's so much data, there's got to be something significant going on there, okay? It's at least something that is worth investigating further. And then, kind of the extreme here, we have no correlation, all right? Your points are just all over the place. There's no pattern apparent here. There's no correlation, okay? Now, correlation, the strength is measured on a scale from -1 to +1. And it's called, we use what's called a correlation coefficient. All right, a correlation coefficient, if it equals -1, that means we have a perfect negative correlation. A +1 would be that first example we saw at the top, perfect positive correlation. Okay? But then we also have 0. This right here would be at least close, really, really close to 0 with no correlation. Okay? Yes.
Is there a difference between having a negative correlation and having a t-test, like a t-test? This t-test like shows difference, but if there's a negative correlation, like what's going on?
No. You're talking about differences versus correlations. They measure different things. What a negative correlation just means that as this increases, this is going down. For example, let's say we're trying to discover if getting more sleep would help you get sick less. So we track the number of hours you got, the average hours someone got sleep over the course of a month, and the number of times they got sick over the course of the month, or the number of days. If we saw that the more they slept, the fewer times they got sick, then that would be a negative correlation. Okay, so there's still a relationship.
So I don't understand how a t-test decides what's the difference.
How a t-test what?
It shows you that the two sets of data aren't the same data.
Sometimes they're called the difference of the means. Obviously, if you took all the data and you found the mean of both of them, they're probably not going to be the same. But is that significantly different?
So your t-test has to be a certain value. Like if it's like above.
Well, there is a range that it would have to be in order to indicate something significant was going on. Yes.
This took out a little way.
Yes.
Are we going to have to, at any point, in order to help determine correlation, do linearizations in this class?
Do you mean like manually find the line of best fit?
Like take something that has a curved fit and then linearize it so that you can display it as just a straight up positive correlation?
No.
I get it. Okay.
All right. So I already mentioned this as we were looking at the moderate or weak correlation. There are outliers possible. Now, here's something, when you're talking about an outlier, notice this. Even though it's way far away from the general body of data, okay, it's on the same linear trend. So we would not call this an outlier. What we call an outlier are the ones that are quite a ways away from the line of best fit. Okay? And as we mentioned a few days ago, any outliers that you get in your data, you should include. Okay? In order to really handle the data properly, you should include outliers as long as they are not the result of an error or a breakdown in the process. Okay? Like we said the other day, if we were running a race and someone tripped, that would obviously be an outlier. We could eliminate them from the data because the test was faulty or running the test was faulty there. Okay? So, real quick, I want you to take a look at these 6 graphs and try to kind of categorize them And really what I'm focusing on primarily are parts 1 and 2, okay? How would you describe these, okay? Is there a pattern, positive, negative, or no correlation? And then, would it be strong? Is it zero? Is it weak, moderate, or strong? Okay? Take a minute here to try to classify these. Okay? Just write them down real quick.
C.
Now, how like, if you're saying that something's symmetrical, it doesn't really have to be perfectly symmetrical. If you want to say that something's perfect, does it have to be perfect?
Yes. So you would just say strong. Yeah. Just like to actually say zero, theoretically, you're going to get something. If you ran a test and tried to determine correlation, you'll get something. To actually get zero is basically impossible. So you just say very, very weak or close to zero.
Well, yeah, like in particle physics, for example, you can say you're certain of something if it's 5 sigmas. Anything that's less than that, you can't say certain.
Yeah. When you're talking about confidence intervals and that kind of thing, we could be 95% or 99% confident that this is the case. All right, so let's do A. William, how would you describe A?
I said no correlation and then 0.
Okay, no correlation, 0, or really, really weak. Okay, that's the technical term, really, really weak. You guys need to lighten up.
Oh, that was good.
Yeah.
So good. Thanks, God. All right, how about B, Ashley?
I look up there some moderate positive correlation.
Good. Moderate positive correlation. That's pretty good. All right. Hannah, how about C? Moderate negative. Okay. Here, this one, moderate's a good pick for this one if we're trying to do a linear.
Yeah, it's not.
This is kind of it kind of fits this quadratic kind of style that you actually can do quadratic lines of best fit. Actually, if you remember your mid-year assessment last year when you did the stuff with the Ebola numbers, you did an exponential and you did
Logarithmic.
you could do something like that, okay? But if you were trying to fit this to a linear relationship, then yeah, this would be a moderate negative correlation, okay? How about D? Tony, can you do D?
I said positive and moderate.
Okay, good. A positive, moderate correlation. We could draw a line of best fit in there, and the points are pretty close to it. Okay. Let's see. Alina, how about E?
I think it's based on the correlation.
For this one?
No,
Oh, the last one. Okay. Yeah, this one, we could say that that's probably a weak positive correlation.
Attention please. This message is for 12th grade residential students only. There will be a college advisory meeting in Lakeside Lecture Hall today, immediately after school. Please be there. Thank you.
All right, good. All right, so there's F. How about E? Alec?
I'm feeling strong negative correlation.
All right, good. Strong negative correlation.
One outlier.
We got this outlier
Super
here.
linear.
Okay. So that was the, maybe we forgot to eliminate the one who tripped or something. So good. So that's the general pattern that we've got there. One of the things, though, we need to make sure that we are very, very careful about is not implying, especially when we're talking about correlations, not implying any kind of causation. All right? As you read a correlation, we need to make sure that we are not inferring any kind of causation. If you do the correlation test for your IA, you need to make very certain that you do not imply any kind of causation. But what do we mean here? Okay? What we mean is that just because two things are related does not mean that there is any kind of cause and effect. All right? There's a couple of kind of silly examples that your book gives, but it proves the point really well. Okay? Arm length and running speed, okay, of young children were measured, and a strong positive correlation was found to exist between the variables. Okay? Arm length and running speed. Okay? What do you think about that?
Like, that makes sense, but it doesn't mean that if you're born with long arms, you're gonna be a fast runner.
Okay, well, why not? We have a correlation. There's a relationship here.
Because
It actually, hang on.
There should be a very weak correlation.
We're talking about young children. Remember that part.
Yeah, well,
So don't debate the data. Okay, let's debate the
No, it's
what the
because-
data tells us.
the stronger, longer arm length could mean longer legs, and that means that they're gonna run a little faster, but it's gonna be a really small value at a very weak correlation, but there ought to be some correlation if your sample size is large enough.
Okay. Well, here they actually did get a strong correlation. Okay. Okay, we're talking about young children, and actually, but you bring up the point that's really at the key of this. Are the long arms really what's making these kids run faster? You know, they got these big long arms, they get so much momentum going, and it pushes them faster,
It
right?
stabilizes them
No.
a little better, but that's not the big part.
What happens? Or what is more likely the reason why these kids are able to run faster? Yeah, typically kids don't have really long arms and then real short legs, okay? And vice versa. Typically kids don't have really short arms and real long legs, okay? They grow pretty much symmetrically when they're little, at least, you know? Sometimes middle school lends itself to some oblongness, but,
Those backpacks.
yeah. But anyways, here's the idea, okay? There's another variable which is age, and there's another variable of the length of the legs that come into play here, okay? Those are more likely causes, even though there's a relationship.
Wait, so you think that if there's a correlation, it just means that something else causes it?
No,
Always.
not necessarily. That's the thing. A
I thought it was
correlation,
just a coincidence.
there could be a cause-effect relationship, but this
don't know.
does not prove it.
No, I know, but you're saying that it's not cause and effect on the grounds that it's probably their legs.
Well, in this example, yeah, probably it's more likely, since your legs give you a longer stride and whatnot, that's more likely to be the cause of faster running. Okay? So, all right, we'll see you guys